Yeah, so now we'll go to the next step. We'll look at how the CPU boots and how essentially the operating system essentially gets loaded up, right? And very specifically, we are again going to be talking about the embedded device. Though in a PC or a server, it's not too different. There'll be certain changes, there'll be certain additions and checks which are actually done. But we're going to keep things simple and just going to look at a very simple embedded device, right? So here, for instance, is your embedded device, and here is a reset switch. So when you essentially press this switch, so it's a push button switch. So when you press it, it creates a signal of this particular form, and this signal is then connected to your microprocessor, to your CPU, and very specifically to the reset pin of the CPU, and it would essentially indicate to the CPU that your processor is going to be reset and should start executing, right? So we'll go through what happens soon after this particular pulse is set to the processor, right? Is sent to the reset pin of the processor, right? So this is essentially indicated by this power on reset, right? So power on reset is essentially this particular pulse given to the reset pin of your processor. So when the processor essentially receives such a pulse, it would set all the registers present within the processor to have a value of 0, or in other words, it just resets all the registers except the PC, right? The PC stands for the program counter. Now, why is the program counter important, and what is this program counter register? The program counter register essentially is a register which points to the next instruction that needs to be executed, right? Now, all other registers are set to 0 except the program counter, which is set to a value known as the reset vector. So, in other words, and very specifically, why it's called a reset vector? Because the first instruction that gets executed by the CPU is going to be present at this particular address known as the reset vector. Now, what is present at the reset vector? So, to make your computer or to make your processor function properly, at this reset vector address, you would require some code, right? And this is typically called the bootloader, right? Now, so the bootloader is a small set of small program that is present at the reset vector, which starts to execute, and depending on the functionality of your embedded device, could either execute some software like so this is called bare metal software because it does not have an operating system. If your embedded device has an operating system, then the bootloader would essentially start loading the operating system. The OS would execute and then eventually start loading the applications, start processes, and the rest is of course well known, right? Now, this is what happens in an embedded device. If it's your regular PC, you would still have something like a bootloader, but after the bootloader, you would have another step known as the BIOS, which performs a lot of initializations of memory, different peripherals, tries to identify what is connected in your device and so on, and also does some security checks to identify what kind of software is present, whether the operating system that you're executing is a valid operating system, it's not been tampered and so on. And finally, the BIOS would load the operating system. But to keep things simple, we are just going to follow this particular process, right? So power on reset, your CPU is essentially set to 0 except for the program counter. The program counter is set to this reset vector where so the reset vector is an address present in your memory, right? And the reset vector essentially has a small program called the bootloader which would load your operating system, right? Right. Okay. So I'm just going to take a detour now because I'm going to talk about how about something very specific to QEMU. So we've seen essentially what happens in a device when it gets powered on. Now, when we are working with xv6, we do not work with any physical device like this. Rather, we work with something with an emulation of this physical device, right. So, we are essentially working with an emulator, right. So, what is this emulator? So, the emulator, which is the emulator we will work on is called QEMU, QEMU, is a piece of software which kind of emulates a particular hardware system, right. It emulates a processor, it could emulate different peripherals and so on. Okay. So, the reason we essentially use this kind of emulator is the fact that it can be easily tested, and it's a perfect kind of environment to essentially learn and try out various kinds of experiments to look at the functionality of operating systems. So, QEMU is an emulator on which we essentially have the bootloader, and then run the xv6 operating system, right. So, to keep things simple again, and as is typically done in many embedded devices, we just support a very few set of peripherals, right. Two peripherals that we support are the UART controller. So, the UART controller is essentially emulated in the QEMU. So, this would be a UART controller, right, and also a hard disk controller. So, your the files that so your hard disk controller essentially emulates a hard disk, and all the files that you essentially store from your xv6 operating system is essentially stored or managed by this disk controller. The UART controller, on the other hand, can be used to transmit or as well as receive information. So, this information is read into the xv6 operating system, and then it is transmitted to the application or received from the application. So, what we assume over here is that we have a keyboard that is keyboard is at the receive. So, we have a keyboard connected to the receive, right, and this transmit of the UART is essentially connected to a terminal, right. So, a very simple terminal over here is used as the display for your xv6 operating system, while the receive part of the UART controller is used as the controller. So, what we are going to have over here is that through a simple terminal which we can essentially run, we could essentially send data into the xv6 OS through the QWAT's UART emulator, a UART controller, which then goes, which is read by the xv6 by the device driver in the xv6 OS, and then is then processed. So, every time we do a printf, for instance, the other thing happens, right. So, we want to do a printf, say hello world, it goes into the xv6 OS and then gets transmitted into the terminal, right, through the UART controller and is displayed on the terminal. Okay. Now, the good thing over here is that both the xv6 operating system as well as the QEMU is all open source. So, it can be downloaded, installed on your system without any problem, right. And since it is open source, we have the xv6 operating system code. So, we can actually dig deeper and actually identify various functionalities of the operating system. Okay. So, we now look at powering up the xv6 operating system on QEMU. So, QEMU is the emulator, right, and as we have discussed, every system would have every system would essentially have a memory map. Okay. We will look at more into detail about the memory map of QEMU at a later time, but for now what we would essentially see is that the reset vector for QEMU is at this location 0x1000, right. So this is internal in QEMU, right? So what it actually means is that soon as you start QEMU, it emulates a reset vector to the reset pin of the processor, and all registers within QEMU, within the emulation QEMU, is set to 0 except the program counter, which essentially points to this location 0x1000, right. Now in this location 0x1000, you just have one instruction which essentially jumps to this location 0x80 million, right. So your bootloader and xv6 and so on are essentially present at this memory location and would execute, right. So one thing, one quick thought over here is that if I want to connect this to this particular figure, this entire thing is emulated by QEMU. The reset vector and this where the bootloader is present and the xv6 operating system is present is going to be available in the read-only memory, right. So this location 0x 80 million, right, is 0x80 million should be mapped into this read-only memory, right, typically. So let's see over here, right. So when we execute xv6 on QEMU, this is the sequence of steps that are going to occur, right. So there is the power on reset as usual. So this power on reset is actually triggered when you start QEMU, and all the registers are initialized to 0 except the program counter, which is initialized to 0x1000, and this is then in the so 0x1000. So at so the 0x1000 is essentially the reset vector, which has an instruction which then jumps to the 0x80 million, right. Now this location 0x80 million is the start of this of your kernel, right, and essentially has is essentially implemented at this point in this file called entry.s, right. And then there is a sequence of operations in start.c, main.c and init.c, right. So what are all of these operations, right. So to understand this, as I did mention, xv6 is an open source code. It can be downloaded. So at this particular site, xv6, so you can essentially obtain the source code from this particular website, right. So the entire code is essentially downloaded. I've already downloaded this particular code, and it's present and executes from my system, right. So once you download the code, you would essentially get a directory like this, xv6 riscv, right. So this over here is the entire xv6 operating system, right. This back here. Right. Now right, so what you see, there are many files over here, but some of the important things is present in the kernel, right. And so here are the source code, or a major part of the source code of the xv6. So it has various files, and many of these files will actually see through the course, like the memory management, which is in vm.c. There is a scheduling of a file like, where is it? Yeah, like fs.c deals with the file system, exec.c deals with executing programs, and so on. But in addition to this, you would also have some assembly code, right, which is of the form, I think, right. So there are a few assembly codes which are also going to be part of the kernel. Okay. Now this entire thing is the source code, and of the kernel, and one can and here is a make file, right. So we'll have a separate tutorial on how to essentially build this xv6, but for now I will just show you some things more important. The first thing to actually note is that if I run this make, what is it? Okay, right. So if I run this command called make, it essentially compiles all the source code of my kernel, and then finally generates a particular file called kernel, right, here kernel. Okay. So this kernel is essentially my compiled xv6 kernel. Okay. So now let us actually come back to our presentation, right. Now this compiled xv6 kernel should be somehow placed in this memory location 80 million, right. So when we typically write programs, we don't really bother about where the code is placed, where data is placed, where is the stack and local variables and so on. But when we are working with the operating system, it's critical that the OS is essentially placed at a location which can be reached by the reset vector or the bootloader, right. So in this very specific case, we want to ensure that our xv6 code is present at this memory location 80 million. So how do we do this, right? So, oops, what happened? Yeah. So the way we go about it is by something known as a linker script. Okay. So there is in this particular directory, there is a something known as a kernel.ld, which is essentially called a linker descriptor file, right. So the linker descriptor file essentially gives information, a lot of information about how the various parts or the various sections of your program, of your final executable, should be placed, right. So here, for instance, and I can essentially go back to my slide because I have a slide for this. So this is the structure of your kernel.ld, and what we essentially see over here is that we have this symbol output underscore arc RISC-V, indicating that this is a RISC-V executable, and then we have various sections, right. Now very important for us is that this particular line, which is dot equal to 0x 80 million, right. So we say that at this memory location 0x 80 million, we have the dot text section, right. Now the dot text section is essentially where the code of your kernel essentially resides. So starting at 80 million is where you would have your code, right. Now there is again another dot equal to align 0x1000. That is, the 0x1000 is essentially ensuring that at the end of the source code there is it ends at a boundary of 4 kilobytes, and then there is another section known as the tramp section, stands for trampoline. We'll get into details about what this means. Okay, and in a very similar way, we have sections for the data and another section called the dot bss, which is essentially used to and another section called the dot bss, and finally a marker called the end, right. So this particular line or this particular indicator called etext provides the end of the kernel source code. So it is an etext, stands for an address where the kernel code actually ends. Similarly, this particular end stands for an address where the kernel code as well as the data and the BSS part of the code actually end. Okay. Now very important for us is this particular line which is entry underscore entry, right. So what this line essentially means is that this underscore entry stands for a function which is the first function to execute. Now notice this point here is essentially different from what you're used to with your C programs. Like typically when we write a C program, we know that the first function that executes, or what we learn is that the first function that executes is essentially the main function. But actually speaking, in this operating system, we can actually change the first function to execute, right? By specifying that underscore entry as my entry point into the program, I am trying to indicate that the first function to execute is essentially the underscore entry function. Okay. Now another thing I'll show you. We don't need to go into details of this, but another thing that I would like to show is the is where this particular kernel.ld is utilized. Okay, so where is it utilized? Yeah. So during the compilation, that is during the make, right? In this in this particular line, we see that RISC-V underscore unknown underscore elf ld. So in this, we see that we are given a kernel / kernel.ld. So this linker descriptor is given as input to this command ld, which is essentially your linker part of the compilation, and therefore your linker knows how to place how essentially the kernel should be placed in memory, what is the entry point, where the data should be present, and so on. Okay. A quick note over here too is what is this RISC-V64 unknown elf ld, right? So this essentially is the linker, right? So RISC-V64 unknown elf corresponds to a cross compiler which executes on my Intel platform, my Intel processor, and creates a code for the RISC-V platform, the RISC-V64 platform, right? The output of this particular command is the output of this this ld command is essentially specified by this -o kernel, right? So the executable is called the kernel. The final kernel, which is essentially built after all of this compilation process, is essentially stored in this particular file called kernel. Okay. If I essentially look at the contents of this kernel, I could look at the instructions present in this particular kernel, which is present in this particular file called kernel.asm. Right. So we see a large set of instructions of machine level code or very low level code, right? But we don't need to look into too much detail, but what I want to essentially point out is the fact that at the location 0x80 million is where we have the function called underscore entry, right? So again, indicating that the reset vector is at 1000, 0x1000 in QEMU, and from there it jumps into 0x80 million, and at 80 million we have this function called underscore entry, right? And from underscore entry there are a lot of things which we will get into detail, and we'll see how the kernel essentially boots up.